Hello, ladies and gentlemen. How are we doing this afternoon, evening, morning, whatever time of day it is? Oh, good, good. Yeah, I'm doing fine myself. Thanks for asking, everyone. Yeah, thank you. Okay, so let's start our lesson 2 for R. I'm going to go a little bit faster than I did last time, just a little bit. Hopefully you've downloaded the script already. So go ahead and open up R and open up the script if it's not open already. So we're on lesson 2, and this is about vectors in R. And I know that word vectors scares a lot of students, but I'll explain in just a little bit. So the goal of this is to learn how to use R to store vectors. We will learn how to use the R console to store single numeric values, storing numeric data, that is a vector. We'll learn some common statistical functions for numeric data, ones that you may have already learned. We'll create sequences, and also we'll talk about storing categorical data and also making frequency tables. Okay, so 2.1, storing single values into R. Okay, there's actually 4 different ways R stores the data, and this is where I was alluding to earlier. But there's 4 different ways. One is called vectors, that's what we'll be doing today. The second one is lists, and they're a little bit more complicated. There's matrices, which we'll learn later in the course, and also data frames, which we'll also learn later in this course. So in this section, what we'll be starting out doing the next couple lessons is just using vectors. As I said, we'll see the other 3 later. We won't see lists too much, but we'll see some applications of those. So the best way to think about vectors in R is to think of them as a list, as a set of all the same variables. So if I'm collecting heights, every single number in that vector should be somebody's height. Should be, whether it's in inches or centimeters, we want them all uniform. Much like we've been doing in most of our classes so far. So let's start out with storing a single numeric value in R, and it's just as easy as we come up with what we call a character, and then we store it as a number, or I should actually call this an object, not a character. So in this case, the object A, I'm going to make equal to 10. What does that mean? That means now if okay, notice something. When I hit that line of code, nothing happened. I shouldn't say nothing happened. We did go to the next caret there. And that's actually a good sign. The fact that nothing happened means actually there were no errors. So if I hit this number A and just hit enter, you'll see here the number 10 comes up. Why? Because that's what I told it. Every time you use the letter A now, it's going to be represented by the number 10. So for instance, if I were to do something like A plus 5, well, that should be 10 plus 5, and indeed it is. If I should do something like 3 times A, that should be 30, 3 times 10. And just a big be careful, I was mentioning this earlier, if I go 3A, it's going to say, what are you doing? Again, to multiply, make sure we do that Shift 8 star. Or I could do, I can divide 50 divided by A. Should get me 5, right? 50 divided by 10. And indeed it is. So it's that simple. Now, in older versions of R, instead of using the equal sign that we're used to, I wouldn't say we're used to, that we just learned, they actually use this little symbol here, the caret and a hyphen. And that pretty much represented the equal sign. So if I do that, it still works in R. Looks a little scary, but in fact, you see there I stored B as 7. So why do I say that? It's obviously going to be easier to use the equal signs. It's number 1 more intuitive, and number 2 it's exactly half of the buttons that you have to press. You only have to press 1 instead of 2. But why do I mention this? A lot of times you're going to find later you might want to search how to do something on R, and you might see somebody else's coding. And a lot of older timers, I don't want to say that they're old, but old timers as in they've been using R for a while, will use this symbol for an equals instead of the equal sign. So again, yeah, B got stored as 7. That means if I do 3 times B here, yeah, it should be 3 times 7, 21. Indeed, it is. That's just great. Well, I could keep going with this. I can go, okay, what's B squared? What should it be? Good, 7 squared, 49, right? Yeah. How about, let's go crazy, log of B. What base did I put? 49. Uh-oh, do you know what this is? So we're actually saying log base 49 of B. B was 7. 49 to what power equals 7? Good, 1/2, right? Square root. You guys are logarithm experts, aren't you all? So far I've just been using one letter, A and B, but there's no reason I can't use more than one letter. So I could call it something like dog. I could go dog equals 10. Kind of weird, but if I type the object dog, dog is going to be 10. So if I want to do something like, I can even go crazy and do something like dog to the 2nd power. Hey, that should be 10 squared. Yay. What is the log of dog? Base 10. 10 to what power equals dog, which was 10? 1, right? 10 to the 1st power equals 10. Or I can take the square root of dog. It sounds kind of weird, but I'm just doing the square root of 10. And that's 3.16. Smashing. I'd mentioned this in the previous lesson, but remember not to use commas in our numbers if we're trying to represent a number like 100 million in this case. So I'm creating this new list or new vector called delicious fishes. It's gonna yell at me. Why? Because we got these commas in here. So we can fix that simply by not using commas. And then if we want to, we could take the square root of delicious fishes. They're the best kinds of fishes, aren't they? And the square root of 100 million is 10,000. Right. Okay, so besides using numeric values, we can also store categorical data into R. However, we have to be a little bit careful. If we simply write out the word, R interprets this as a stored vector. So we're going to need to use parentheses when entering categorical data. And what do I mean by that? Okay, for instance, let's do this. If I have a new list, let's call it H, and I say H equals dog, because maybe I asked somebody what their favorite animal was and it was dog. Okay, it seemed like nothing happened there, but we have to be a little bit careful because I already stored dog, didn't I? Dog was 10. So what I've just done is this new list H I've created isn't the word dog. Not at all. It's going to be the number 10. Okay, so what do I mean by that? So let's try something new. Let's say we ask somebody and they liked cats, of course. Whoa, what did happen here? Wow! I don't even know what happened. Did that happen to you? Function file, wow, is as if. So this is some kind of function. I don't know if you got this. Whatever cat is, I can hit cat and hit enter and see what. Whoa, did it just disappear? Oh, whoa, something weird is going. Oh no, it didn't disappear. It just came up again here. It looked like it disappeared, but see, I hit it 2 times. That was the first time. That was the second time. I don't know if you have this. I don't know if this is a function I happen to pick up somewhere down the line. But this is something we want to ignore. So the idea is if I want to enter cat as in like a categorical data, no pun intended. Okay, maybe a little bit of pun intended. If I put quotes around the word cat now this list C is stored as the word cat. Again, not this function cat, which is just crazy. Do you have that on your computers? Did you get the same thing I did? Yeah, I don't know. Internal cat list. Meow. All right. So now there's not too many mathematical functions we can perform on this vectors yet, and the reason why, we'll start figuring out how to do mean, median, and square roots, standard deviations, variance, all sorts of different functions on our vectors. But for right now, we just have single numeric vectors. So let's learn how to store whole lists or vectors of data. Again, I'm trying to avoid using the word lists because the word list in R has a specific definition that we haven't quite got into yet, and it's a little bit different. We're storing vectors right now. As I mentioned, lists are something else. So let's suppose we did take the height of 25 classmates in our class, and we recorded those heights in inches because going 5'10" is a little bit annoying. So to store multiple values into R, we're going to use this C function. And I kind of think, I don't know exactly what the C represents, but I just think comma. It just helps me remember comma. I don't know. And we're going to separate each observation with a comma because of it. So here we go. Copy and paste this guy here. So let's say, we record the heights of our classmates, and for instance, the first person was 65 inches, that's 5'5", 67 inches, 61, etc., etc., and hit enter. And again, it looks like nothing happened. There was this little plus sign that came in, and that plus sign actually kind of came in here because there was two separate lines when we did this. When you copied it, so that plus sign should be in front of the 67. Indeed it is. It's okay. But again, no error codes came up. It just went smoothly to the next line. That's a good sign. That means you did everything right. And in fact, I can see whether it actually stored by just calling or printing the list we say. And indeed, look at that, 65, 67, 61, 70. Everything is in the exact order that I had put it in. Phew. And again, you can also use the function print heights, but you see it's the same exact thing that I just did by typing out the word heights. Once upon a time, you actually had to do this to see what's in your list, but now R has been made a little bit more user-friendly. Okay, so this is one way of storing data. Now I do this a lot, make all these lists, vectors that is, using the C function. And it is a little time consuming. Maybe it's just really to separate the commas, or if I'm doing something like copying and pasting. If I'm copying and pasting a bunch of numbers, well, say it's my homework assignment, that means I have to go back in there and for instance, go back in there and maybe call this, I'm just going to call this a new list, H, and then I have to put a comma here and a comma there, and boy, that gets time consuming, right? It's going to give me an error here, and that's fine. I'm going to leave that alone. It's giving me an error because I didn't finish putting in all those commas. So there is an easier way to put in data without using that C function, and that is to scan. And so we'll see how the scan function works here. We're going to start with going just putting in a list. So I'm creating a new object. I'm going to call it just X. And I'm going to hit X scan, and I'm going to leave this parenthesis completely blank. Why did it do that? Let's try that again. I'm just going to type this in manually. Scan, X equals scan. And then we're going to get this number 1 that comes up. What that's kind of saying is like, hey, I'm ready to put in numbers. And the beautiful part is now I can copy and paste a list of numbers as long as they're separated by a space, or in this case, multiple spaces, or, one space, a lot of spaces, 3 spaces, 4 spaces, whatever, that's fine. It's going to end up reading these, so let's just see how this works. Remember, I hit X equals scan, and that number 1 came up. if I hit enter right now, this number 19 shows up. What it's actually asking is like, well, there must be 18 elements, 18 numbers that I just stored, and it's kind of going, well, what's the 19th number? Or if we're done in this case, hit return again, and it'll tell you exactly read 18 items. Now if I print this back out, or if I just hit X, you can see there's all the numbers. And again, we mentioned last time our ignore spaces, so those spaces between, for instance, 41 and 45 up there is completely ignored. So this is our list. We've created a new vector called X here. And what's kind of nice, before I use the next lines of codes, is there's a lot of different things we can do now. For instance, if I do something like x plus 10, what it's going to do is it's automatically going to add 10 to every single number in my list. Seeing it there? Every single number got added by 10. I could even do something like x squared, x to the second. It's going to square every single number. The numbers might get a little big, but wow, 1843, is that 43 squared? I can double check that. Yeah, we just squared every list here as well. I can multiply, I can double every list. I can do 2x. Now notice as well here, as I was doing these operations, I didn't store these as anything. I just asked it to tell me what 2x is. I could, for instance, create a new list called y, or a new vector again. Now I could do y equals 2x. Now again, it looks like nothing happened, but it went smoothly to the next line. And this means now y is now officially stored every time I call up y. That it's 2x, so it's 2 times 43, 2 times 43, 2 times 45, 2 times 47, etc., etc. So one way, so going off of that, for instance, the heights list that we had just stored, these were the heights of our 25 classmates. Suppose I wanted to convert these to centimeters. Well, if we recall, there's 2.54 centimeters in 1 inch. So if I'm going from inches to centimeters, I multiply my inches by 2.54. If I ever need to go from centimeters to inches, I'm going to divide my centimeters by 2.54 to get inches. So what I can do is create, let's say, a new list, heights, and I'll call this cm for centimeters, and taking 2.54 and multiplying it by every height in inches, and then what I should get is all those same heights in centimeters. So if you're 5'5", for instance, if you ever go to Europe or Asia or anywhere else in the world that uses the metric system, you're not 6'5". I'm sorry, 5'5". Oops. You're 165 centimeters essentially. I am 75 inches. Let's see if I'm up here. 6'3". Oh, I'm not quite up here, but in case you're interested, and I'm often interested because I forget, I am 6'3". I'm 190 centimeters or 191. Yeah, I'll round down because I'm like. Okay, I apologize. I don't know where my video cut off, and I got to get used to this. I think hopefully I was talking about storing the heights into centimeters, and hopefully I just did that. Okay, so we were, again, I apologize, I don't know where I left off. My iPad falls asleep and stops recording somewhere along the line, and I'm not sure exactly where. So I'm going back to heights in centimeters. We took this list heights, and the idea was, how do we convert this to centimeters, let's say? Well, there's 2.54 centimeters in an inch, so if I take every single inch and multiply it by 2.54, I'll have my heights in centimeters, which is what I did here. And there's an unexpected comma because or unexpected caret or greater than sign because I copied two of them. Whoops, Yeah. Man, everything was going smoothly until all that happened. Okay, 2.3. Let's get into the next section here. And you, iPad, stay awake. Okay, so some common statistical functions for numeric data. So did your mean stats teacher ever make you find the min, Q1, median, Q3, max, mean, standard deviation, variance by hand? Yeah, it was a lot of work, wasn't it? Especially if I gave you the list out of order. You have to put everything in order, count how many numbers there are, find the median, find this, find that, and all of a sudden your head explodes and you wonder why, what kind of jerk-faced teacher would do this to you when the whole time you could do it on a calculator easier, or let's say, in this case, R. So let's talk about how to use this. Anytime we have a list, we can perform these and many more functions, but some common ones that we'll talk about is the mean, standard deviation, variance, min, max, median, summary, that's going to be the 5-number summary, sort. We can sort either from smallest to largest or largest to smallest, and we could find, for instance, the length or the sample size. Again, this is just a few of many different functions we can do on a list. A vector, that is. In fact, I have a vector stored. It's this vector x. I don't know what it represents. That was the one that we scanned in. But let's try some of these. Let's see what happens if I find the mean of x. Looks like most numbers are somewhere around 40, low 40s, so hopefully the mean of x is somewhere around there. Bam, 42.333. We could find the standard deviation of x. So standard deviation is just as easy as SD, standard deviation, and just barely under 3. We could find the variance of x, and that's going to be the var, and I'm going to bet you it's just a little bit over 9. Indeed it is, and I'll tell you why I knew that in just a minute. We could find the min, the max, so the minimum value of x in case I didn't want to find it. The maximum value of x was 48. We could do the median of x. The median is 43. In fact, I think it's even easier to use the whole 5-number summary that we learned in class, which was the min Q1, the median Q3, and the max. And you'll see all of them there. In fact, it even includes the mean. So the minimum value was 36. Q1 is 40.25, and I'll talk about that in just a second. The median was 40.3. The Q3 was 44, and the max was 48. So if I wanted to sort the numbers, I could sort them in order of smallest to largest. And there's the numbers sorted. If I wanted to find the length, or that is the sample size, because I didn't want to actually count, this is actually very useful a lot of times. This tells you the sample size. There's 18 different numbers in there. So I want to go back here to the 5-number summary and just kind of, I may have mentioned something like this in class before, but it's really about finding Q1 and Q3. So let's actually, now that I have the data sorted here, let's talk about how to find the median. We learned that, hey, if there's 18 numbers, that's n, we could find the median by the spot number it's in will be n plus 1 divided by 2. So that is 18 plus 1 is 19 divided by 2 is 9.5. So in other words, I'd count 1, 2, 3, 4, 5, 6, 7, 8, 9. And here is 10, so that is, it's halfway in between, well, 43 and 43. Well, that's going to be 43. Okay, so what did I tell you then? I said, well, since the median was in between these two 43s, we're going to take this whole side here, and we're going to find the median of these 8 numbers. Since there's 8 numbers, they should be somewhere in between the 4th and the 5th value. Okay, so I'd say here Q1 is clearly 40. How does it get 40.5? And on the other side here, Q3 looked like it was between 44 and let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9. So this should be Q3 now, should be between the 1, 2, 3, 4, and 5, 44. 1, 2, 3, 4, 5. Huh. So, all right. Here's the moral of the story. The Q1 is different than the value R gets is slightly different than the value you've been taught on how to do it. I'm going to just say that's okay. And why, I think I'd mention it becomes a partitioning problem. I have 18 numbers, and I'm trying to separate 18 things into 4 equal quartiles. Well, okay, if that means that all 4 quartiles would get 4 numbers, right? 4 times 4 would get us 16. Well, that means there's 2 left over. There's 2 numbers left over. That means 2 of the quartiles are going to have 5 numbers, and 2 of them are going to have 4 numbers. Which one gets which 2 quartiles get the extra number? Well, it's kind of arbitrary. So again, these numbers are always kind of they roughly separate our data into quartiles. So 25%, about 25% of observations on our list X are between 36 and 40.25. 25% are between 42.5 and 43, and so on and so forth. So I just wanted to mention that now because you'll get slightly different values on Q1 and Q3 using R. Okay, standard deviation. How long have I gone for? All right, so I did mention that standard deviation, we should have learned this, that the variance is the square root of the standard deviation. And let's see what happens if I were to take the square root of the variance. Look at that. I get I get the same exact number as I did with the standard deviation. That also means I should be able to square the standard deviation and get the variance. Ta-da! I did. Are you impressed? Good. Okay, 2.4. This is on creating sequences. A lot of times it's very useful to create sequences. And one way to create a nice easy sequence of say integers is using the colon. So if I'm going 1 colon 5, I'm saying find me the numbers 1 through 5. 1, 2, 3, 4, 5. Good job. It did it. I don't have to start at 1. I could start at any number I wanted. I can go 6 to 10. If I'm feeling particularly crazy, I can go 6 to 100. Whoo-hoo. There they all are in all their glory. This is a good opportunity. I mentioned this in my last lesson. What are these numbers here in the brackets? These are the place numbers. So 1, that means this is the first number. 12, this is the 12th number. I can go all the way down here, 67, this is the 67th number. 89, this number here is the 89th number. And again, sometimes, you know, if you want to know how many numbers there were in there, I can go, hey, what's the length of 6 to 100? Well, there happen to be 95 numbers in there. You thought there were 94, right? 100 minus 6 will get you 94, but we do include the 6, so it's almost like starting at 0 or something like that. So that's a useful function. Now again, I didn't store any of this, so I can easily just store it. Say t is 0 through 15. I could start at 0. Again, looks like nothing happened because it got stored, but I can call it up and there it is in all its glory. I could even go from negative numbers to positive numbers, like -4 to 3. Sure, no problem. What's useful is maybe we're looking for years. Maybe you want to do a time series plot, and we're starting from the year 1990, that was a good year, up to 2015. And there's all the years from 1990 to 2015. So another great application of this. You could also repeat a number multiple times if you so need to, and that's the REP function. And the way the repeat number works is tell me what you want to repeat, say the number 4, and then put a comma, and tell me how many times you want to repeat it, say 10 times. So there's 4 tens. Now this is particularly useful if you have, let's try this list here. B here. This is particularly useful in this case. Let me copy and paste this in. If say I had 3 1s and 2 5s and 3 and excuse me, let me do that again. if I had 3 1s and 5 2s and 3 8s, I could store this. Now notice the way I stored this. I actually stored this as a list. So I needed the C button. Why did I need the C button? Because I was actually repeating more than one number. I'm repeating 1 3 times, comma, 2 5 times, comma, 3 8 times. And if I print out this list, you could see there it is. There's that. 3 1s, 5 2s, and 8 3s. Again, this is useful if you've already maybe taken some data by hand and if you have a lot of repeats, so you don't have to write 1 1 1 1 1 1 2 2 2 2 2 2 3 3 3 3 3, and you know, who knows, you might have made a mistake. Sometimes as well, you have a list, you have a vector b, and maybe hell man, I forgot there was 1 4 on here, but I don't want to have to like repeat all this code. Well, one way of doing this is is kind of overwriting the list. So I'm going to go, okay, I already have a list called B, but I'm going to make the list B that I already had. So it's going to take all these numbers because this was my vector B, and maybe I want to add a 4 to it. So if you kind of think about what I'm doing here, I'm kind of going, okay, this list B, it hasn't stored it yet, is going to be the list, the vector B, which was all this, comma 4. And when you see that, there it is. I added, there's my original B, and there's the number 4. Okay, so I was talking about the colon earlier, and that's nice. The colon's nice, but that only works if we're counting by integers. What if I want to count by like a decimal, or if I want to count by 2s or 4s or 5, something like that? Well, I can use this sequence function, seq. And what I'm going to do, it's going to be sequence, and then my starting value, my stopping value, and what you want me to count by. So this one should be from 0 up to 1, and I'm counting by 0.1. So 0.0, 0.1, 0.2, 0.3, all the way up to 1.0. Pretty nice. I could count, here's another example of this. Here's one I'm storing. So I stored this, and when notice the difference. Here I didn't store it, so I'm just saying, tell me what it is. And in this case, I'm storing it, so it looked like nothing happened, but don't worry, it's in there. And what did I do there? I counted from 0 to 100 by 4s. Sometimes too, it might get mad at you, because if I wanted to count by 3s, I don't think I'd end up at 100 exactly, would I? So I'm trying to remember what it does here. Oh, interesting. So if I counted from 0 to 100 by 3s, I actually don't end up at 100, but it just says, okay, we stop at 99. That's where I'm going to stop. So this is for you trig fans out here. This looks like a unit circle one here. If I want to do a sequence from 0 to 2 pi, I can, and maybe do it in increments of pi by 8. I can do that too. 0 to 2 pi by pi over 8. There it is in all its glory. There's pi over 2. Some of these numbers look familiar. And there's 2 pi. No, doesn't look familiar? Okay, I'm not terribly surprised. Okay, last part of the lesson here. This is about storing categorical data and tables. So far, everything we've done was on numeric data. If you recall, we can't do something like take the mean of people's favorite pet, right? What's the mean favorite pet? Oh, it's dog point cat. Cat point dog, that is. Cat point dog point fish. Okay, so again, we need to be just a little careful when storing categorical data into R, since if I don't put a quote around anything, it's going to think that it's some kind of object, some kind of vector, some kind. Object's a general word. Object could be a vector, it could be a list, it could be a data frame, it could be any of those. So, or a matrix. That's what I was looking for, or a matrix. So suppose we ask 10 people for their favorite pet. And you know, we got a cat, a dog, a fish, a dog, a cat, a dog, a reptile, a cat, and a dog. So if I wanted to store a list, I'll call it maybe favorite pet. Notice how I store this vector every single time. Annoyingly, I'm going to have to put quotation marks around my categorical variable. So there is my fave pet. And if you didn't believe me, type out fave pet, hit enter, and see what happens. And notice how it even stores or outputs these values in quotation marks. So that's telling you these are categorical variables. Anytime you see quotes around something, it's going to represent that it's categorical. It's pretty annoying having to put commas around each term, especially if maybe you're copying and pasting this again off of something, off of let's say a homework assignment. So it's kind of annoying. So here's what we're going to do if you don't want to use those quotes, or if you want to straight up copy and paste. Like before, we're going to use the scan function, although this time we have to be a little careful. So I'm going to create an object called pet, and I'm going to scan. And if you remember when I just had this empty, I could store numbers in here. But if I want to store categorical data, I'm going to go, what? What do you want me to store? And I'm going to put these blank quotes, indicating that this is going to be categorical data, not numbers. Even if I were to put numbers in here right now, it would treat the numbers like categorical data. So for instance, maybe I want to, maybe this was my, these were my responses again: cat, dog, dog, fish, dog, cat, dog, reptile, cat, dog. And I can hit enter. Again, that 11 will come up telling me if I hit enter one more time, it'll read it, and there's red 10 items. So now if I see what happened, you'll see the quotes come up. All the cats and dogs got quotations marks around it thanks to this little what command in the scan function. It is case sensitive. It's a good point here. Because if I were to capitalize one of the dogs and not capitalize the other one, it would read the capital dog different than the lowercase dog, even though we know our intentions are to keep them the same. So we can also use that repeat function, for instance, to throw out multiple, in this case, dogs. So if I wanted to repeat dog 11 times, notice how I am putting it in quotation marks. And I think we had a list already stored as dog, right? So I'm just, yeah, 10. So just watch what happens here, since we already had the object dog stored. If I were to hit repeat dog without the quotation marks 11 times, it's going to repeat the number 10. Again, quotes tell that it's a categorical variable. No quotes, it's some object stored. And in fact, we had a list called X. I'm almost afraid to do this. But let's see what happens if we do repeat X 10 times. I have a feeling it's going to repeat that whole list 10 times, and there it is in all its glory. Okay, that wasn't very much glory, but still. Okay, last thing. Well, we haven't learned how to do terribly many functions with categorical data yet, but one of the most useful is just getting a frequency table. That is, how many people liked dogs? How many people liked cats? How many people liked this or that? And we can use this function table. So table, for instance, pets. We had that list called pets. Just kidding, it was just called pet. And we see here in this case 3 people liked cat, 5 liked dog, 1 liked fish, 1 liked reptile. I would like you to notice how these numbers came out. It didn't come out, the categories came out. It didn't come out by popularity because dogs were first. Can you tell which order that came out in? Good, alphabetical, right? But this table function works on heights too. On numerical data. Kind of like a frequency table. For instance, this was our heights list from earlier. We had some repeats. We had 3 people who were 65 inches, 3 who were 67, 4 people who were 68, etc. What was that one list that we had stored with all the repeats? It was B, yeah. We had that list B that we even created by doing a whole bunch of repeats And if you remember, that was the one where we had 3 1s and 5 2s and 8 3s and 1 4 that we added in at the end. So these are frequency tables. And in fact, if you want to do the proportion, I'll show you one last trick here. Let's go back to our pet list here. So if you want to find, let's say, the percentage or proportion of everyone who likes every pet, what I can do is I can take the table, so that's going to be the frequencies, and divide it by the sample size, and the sample size is length. And what I get out of that is the proportions in this case. And if I want to get one more fancy, if I want them written as percentages, I'd have to multiply all these proportions by 100. So I can do 100 times the table of pet divided by the sample size, and this will get me the percent if I want things in percent here. So 30% of my sample like cats, 50% like dogs, 10 like reptiles, and 10 like fish. Okay, so just to recap the lesson, boy, we learned a lot. We learned how to store data and into vectors. So to store numeric data, we don't have to put commas around anything, and we can just put in the numbers directly. We can use either the C function or the scan function. If we want to store categorical data, we have to put our categorical data around parentheses. And again, we could use the C function and annoyingly put every word in quotation marks, or we can use the scan what function, and that will allow us to copy and paste values off of, say, the internet or your homework assignment. Oh man, this was supposed to go quicker. All right, let's check out your homework here. This will be due in about a week. Let's kind of breeze through here. So problem number 1, we're going to let x equal to the number 32. You're going to perform these operations. Be careful with this one. It has a nice answer. We have a log, so remember log comma base. This is log base 2 of x. Okay, these questions, number 2, let's do number 2. It asks you to use the C function to store the following vector, create your own name for the vector, and you're going to use these in a later assignment. So here's some ages of students in a college class, and if you're not copying and pasting, you're doing too much work. So I do ask you to use the C function in this case. So if I want to store this list, let's say call it age, I'm going to go C parentheses, and I pasted all those numbers in, but now annoyingly there are no commas separating them, so I need to put commas. And notice it doesn't matter exactly where I put the comma because, again, R ignores spaces. So and if there are no errors, if I did it all right, it'll look like nothing happened, but I could just double check that. So so when you do your homework, once you get it to work, copy and paste and put it in, and that looks good. If you want to get crazy, maybe change the color. I don't know, blue sounds nice. Change the color maybe to indicate that that was your code. Oops, this is all part of it too, so I think it's blue too. Okay, so next couple problems. Problem 2, I ask you to use the C function. Problem 3, I ask you to scan these in. It's a lot easier. You don't need commas, and that makes life easier when we have all big numbers like this. Problem 4 is where you're going back to those lists that you stored, and you're finding, say, the mean age. Verify that the mean is the sum of the ages divided by the sample size. I did forget to mention that particular function. If I wanted to, for instance, find the sum, for instance, the ages that I just entered here, if I wanted to find what the sum is, that is if I added all these numbers together, add up to 329. So one way you could actually find, for instance, the mean, if you didn't know there was a function called mean, we know it's the sum of all the observations divided by the sample size, which is the length. This is one annoying way I could find the mean of the ages. Of course, equivalently, I could just do mean, but I'm going to ask in one of the problems that you verify that. Finding 5-number summaries, hopefully that's okay. So part B, this has had to do with all those heights in centimeters. This is 7B. Given that 1 inch equals 2.5 centimeters, I'm going to give you a little hint. Since the heights were given in centimeters, we're going to have to create a new list, and actually whatever you call this list, divide it by 2.54, and then you'll convert centimeters into inches. So again, divide your centimeters by 2.54 to get inches. Okay, there's some sequences. Hopefully you can get these. This one's a little annoying, but number 11, this is some categorical data going back to pets. Number 12, some categorical data from intended majors in college. And then 13 through 17 is things like fix the errors. So hopefully you can do that. Just a heads up, number 15, you got to do this 2 at a time. One line at a time, because we have to hit the scan function first, hit enter, and then we try to enter this. So hopefully you can do these, and thank you for your time.